All right, so today's subject, 2D and 3D finite element methods. As kind of demonstrated in this problem, we really want to extend all the things that we've talked about in this class up to now into this more exciting domain of these, 2D planar problems or three-dimensional solids. And we're going to use all the same machinery and all the same approaches. It's just going to look a little bit more complicated. So to really understand how do we get to the point of solving and assembling these finite element systems of equations for 2D and 3D domains, we have to go all the way back to the early part of the class where we talked about governing differential equations. And in particular, in the case of governing differential equations for solid media or solid mechanics, if you like, we derived already this set of equations, which effectively characterized the pointwise statement of equilibrium that must hold for every point in some body of interest, which I'll call omega. And this description of equilibrium in this differential equation format actually was the synthesis of all of these different relationships that we had previously come up with. We had to have some continuous or compatible displacement field characterizing the motion of individual material points, and the motion of those points had to be defined in such a way that no part of the body should split apart after deformation occurs, which implies that these displacement functions have to be continuous functions of position. In the case of this now more general three-dimensional context, you can still have a continuous function defined over some more complicated geometry, a 2D or a 3D domain. So the notion of continuity of functions still applies in that context. But we had to come up with more general descriptions of what displacement meant. Displacement wasn't just axial displacement in these one-dimensional problems. Now, displacement is really a vector of components of displacement which might occur in the x, y, or z directions. That complication led to also having to come up with a more general description of strain, where strain in the one-dimensional setting was simply the derivative of the displacement, the axial displacement field with respect to axial position. Now we had to come up with this more general description of strain as being some characterization of the displacement gradient, which itself is a 3x3 array or a tensor. And specifically, in the case of linear elastic deformations, we could define this so-called small strain tensor, represented by epsilon, also a 3x3 array, but it's symmetric. And in fact, it's defined as simply the symmetric part of this displacement gradient tensor. We also came up with these relationships between strain, this 3x3 array or a tensor of strain components. We have related those components to the resulting internal state of stress in a material through this linear elastic constitutive relationship. We derived that that relationship depends on this fourth rank tensor, C, written in this math boldface font. But in any case, this rank 4 tensor provided us a way of relating all of those 9, technically 6 independent components of strain to the resulting 9, technically 6 components of stress. Remembering that both the stress and strain tensors are themselves symmetric tensors. So if we wanted to define everything in terms of, the 9 components of strain to the 9 components of stress, really there's only 6 independent components of each of those two things. And then finally, we came up with force equilibrium, effectively a statement of 3 equations governing the equilibrium of forces or sum of forces in the x, y, and z directions, which have to hold in this pointwise sense, and which might involve some body force, force per unit of volume that could act in also the x, y, or z directions. And this differential relationship involved the divergence of the stress tensor, this nabla dot with the sigma stress tensor. We could put all those things together into this one governing differential equation describing elasticity. And if you want to review some of those topics related to this, I encourage you to do so because we're really going to be leveraging a lot of this in the coming lectures. So just to present you with the recap of all these concepts, now we came up with this governing differential equation or really a set of different equations relating all these different quantities of interest in order to express equilibrium in this pointwise sense as a differential equation. But as you might recall, the challenge with doing that is that we have to set up these boundary value problems, right? We have to come up with some description of not just what this body has to satisfy in a pointwise sense, we also had to describe what's happening to this body on its exterior. So we came up with also descriptions of boundary conditions, things that we can prescribe over the exterior boundary of this domain omega. And I'll be specific in saying that perhaps we can break up this exterior portion of the domain. The boundary of this continuum potato omega, I'll call del omega. And I'll also, in this particular example, which we'll use as just a reference for developing some of the later equations in today's lecture, I'll also suppose that I can break up the exterior of this potato into two sections that are mutually exclusive to one another, which I'll call gamma u and gamma t. On gamma u, this blue line, I'll impose displacement boundary conditions. Or in other words, I'll directly constrain what the value of displacement is along this exterior portion of the boundary, gamma u. And on all of the rest of the boundary, gamma t, I might prescribe some traction boundary conditions. That's where I'm actually explicitly stating what are the components of force per unit of area acting on the exterior surface all over gamma t. And I've defined both of these subsets of the boundary of omega such that they don't intersect. They're mutually exclusive sets describing different regions of the boundary. So if I were to take the set intersection of these two things, I just get the empty set or the null set. So they don't overlap at all. And rather, their completion, their union, forms the entire boundary. So I've specified boundary conditions everywhere on the boundary, at every single point along the boundary on del omega. I've specified some boundary conditions, either a traction boundary condition or displacement boundary condition. And nowhere have I specified both of those things at the same time. And if you recall, doing that was necessary in order for us to obtain a unique solution. And in fact, for a solution to even exist. If we had somehow these two things overlapping at some region, then we would be imposing too many constraints on the problem, and we would be over-constraining things such that we wouldn't even have a solution. We would fail to satisfy the conditions of solution existence. And conversely, if I said that maybe there was some hole where I didn't specify any boundary conditions, neither a displacement boundary condition nor a traction boundary condition. If I failed to specify what some boundary condition was there, then I would fail to satisfy the conditions of solution uniqueness. Because who knows, I could put something there and there's many possible solutions which might satisfy my governing differential equation and whatever incomplete boundary conditions I specified. But, you know, with this hole on the boundary where I don't know if I'm specifying displacement or traction, there's any possible number of solutions that I could get out of that. So I have to be complete in describing these boundary conditions everywhere on the boundary of the body. All right. Now, given all these things, a statement of equilibrium expressed through this governing differential equation, and given these sets of boundary conditions, either on the displacement or on the exterior traction that might act on the boundary of this object, I can now pose formally a boundary value problem expressed in terms of the strong formulation of this boundary value problem for a 2D or 3D domain. And it looks something like this. The goal is I want to find what is the displacement field of all points within this body that satisfy this governing differential equation and which also satisfy the displacement and traction boundary conditions. Now, if you remember, when we went about setting up problems like this, as posed in the strong formulation, we had a couple of issues with trying to solve problems when posed in this format. And just to kind of give you an opportunity to recall why solving problems as posed in the strong form presents some challenges, what were some of those issues that we came across? Why did we not like having to solve problems posed in this format? Say you first again. Integration of forces is challenging, and you said integration is challenging. I think, do you have something else? Other kind of suggestions before we kind of like, because there are technically multiple issues. So there's possibility for additional things if you wanted to supplement. Hmm. Say again? Forming a matrix, I guess, is one potential issue. I'll kind of give you some hints. What's a potential issue with the fact that this statement of equilibrium is effectively a pointwise statement of equilibrium? It has to be satisfied, this equation, every just potential point X in this domain. What's the problem with expressing this statement of equilibrium like that? Yeah, there's too many points. There's an infinite number of points at which we have to satisfy the condition. So that's problem number one. We have this infinite number of equations we have to satisfy, and in fact, an infinite number of displacements at each of these corresponding infinite number of points at which we have to find a solution. So infinite number of unknowns, infinite number of equations, that's a problem. There was one other problem with posing problems in this format. Let's see, maybe if you can identify it. It actually has to do with something related to this operator. And it's not quite integration, although you mentioned that the issue of integration is a concern in some settings. But it's actually more to do with differentiation. Can you see any issue with this expression? Yeah, there's some derivatives of derivatives. We've imposed some requirements on the displacement field itself having to be a continuous function. But let me ask you, what if, I don't know, what if this object didn't consist of some uniform material? Maybe it was actually two materials glued together along some shared intermediate interface, such that if I were to define some of these material properties as characterized through this fourth rank constitutive tensor, maybe I could define these properties such that they jump in value as you pass along that discrete boundary. What would happen then if I were to try to take a derivative of some expression that involves some kind of discontinuous representation of material properties? Would I even have a well-defined derivative at the location where the material properties are not even a continuous function? No, so that's a problem, right? It basically means that I have additional differentiability requirements on the solution that I can obtain. And in fact, they're somewhat unphysical in the sense that they impose these kind of onerous conditions on effectively what are continuity requirements on material properties, and also continuity requirements on the derivative of the displacement field or the displacement gradient. So those things really make it, both of those things. The fact that we're trying to solve an infinite dimensional problem is one issue. The other issue is these kind of differentiability issues. So what we really want is to convert this strong formulation of the boundary value problem into a different format that allows us to, number one, try to convert it into an equivalent or kind of simpler problem, which is to say a smaller problem, which we can solve in an approximate sense. And the other issue is we want to get rid of this term that involves having to take a derivative of whatever this term is. And remember that this term is really nothing more than the stress tensor itself. So if the stress tensor itself is not, expressible as like this continuous function or a smooth function, then, we have to contend with this issue. So we want to involve any terms that have some dependence on stress, or more specifically, stress divergence. We want to manipulate them into a different format so that we're not expressing them as involving some derivative of the stress tensor. Okay, so those are the issues. We have, at least when we are solving problems in strong form, we're solving this set of differential equations, but it involves, as you rightly put it, an infinite number of points at which we have to satisfy that condition, so an infinite number of equations, and an infinite number of unknowns for the discrete displacements at each of these infinite number of points. A problem, clearly. So what was the solution? Well, the solution was we had to manipulate this expression going from a strong formulation of the problem into a nonetheless equivalent weak formulation. And that's precisely what we did in the case of the one-dimensional situation. We basically said, let's take this governing differential equation. It has to be equal to 0 everywhere, at every point in the domain. And if it's equal to 0 everywhere, I could just as easily say, let's take this function that's equal to 0 everywhere and integrate this function over the domain, and maybe also weight that integral by some arbitrarily chosen test function. You could think of that test function as being some kind of weighting kernel or some kind of weighting function that measures some kind of weighted combination of equilibrium at a bunch of different points and then all summed together. You could think of that weight function as being kind of like a window function that basically takes out some kind of chunk of material and then poses equilibrium over just that chunk. There's a lot of different ways that you can think of this weighting function. And in fact, it also had yet another interpretation. This test function also had the interpretation as being something like a virtual displacement or a virtual displacement field in the case of describing it as a function. So this test function, alternatively a virtual displacement function, was an arbitrary function. We could choose anything we like, so long as it's a continuous function, somewhat like a displacement field in that regard. But regardless of what function we choose, we know that the integrand, specifically this term, the divergence of the stress plus whatever body force is, that thing has to be 0 at all points. So it doesn't matter what this test function is. If I integrate something 0 times some arbitrary function v, I know I should always get back 0 for whatever integral I pick and for whatever choice of test function. So this expression, as shown here, the statement of the weak formulation, has to be satisfied for any possible choice of test function or for any virtual displacement field. All right, so we posed this effectively a weighted integral average form of equilibrium. Rather than posing equilibrium at discrete points, we pose it in this integral average sense weighted by a test function. And it nonetheless gave us an equivalent statement of equilibrium. It's simply a weakened statement of equilibrium. And really the value of doing this is not apparent unless we make a few manipulations. So as we must, we should make those manipulations to really see how do we get rid of, in particular, this term that involves the divergence of the stress tensor, the thing that was impeding our ability to remove some of those differentiability requirements on the stress tensor. Okay, so to do this, let's start by noting that if we have this expression, divergence of the stress tensor plus some kind of body force vector, that expression in these curly braces is itself a vector valued expression. And this test function, this virtual displacement field, itself is also a vector valued function. It has as many components as the displacement field has components. So in other words, it describes the motion of individual or virtual motions of individual material points that might move potentially in the X, Y, or Z directions. So really, there are 3 components in 3 dimensions of this virtual displacement field. And if I wanted to, I could also re-express this same statement just in terms of index notation with the implied Einstein summation convention enforced. So if you like, you can represent this expression just like it's shown here with bold-faced characters and assuming, tensor notation. But if it helps you to understand how exactly do all these, corresponding indices of these tensors match up, you can refer to the equivalent index notation representation of that same equation as shown on the right here. All right, so now we have this equation, but we have to make some manipulations. And the first one that we have to make is by getting rid of this term that involves the stress divergence. Now, in order to do this, we can actually note that if we had a slightly different expression, something that looks more like the divergence of the stress tensor dotted with this virtual displacement vector. Effectively, what we have is the divergence of the product of two things should be equal to the divergence first of the stress tensor, then dotted with this virtual displacement field, plus the stress tensor inner product with the gradient of this virtual displacement field, which in some sense is equivalent to the product rule of differentiation, or rather its equivalent now extended into this multidimensional vector calculus format. So the product rule of differentiation, you're probably familiar with it in one dimension. It generalizes nonetheless to the case of multivariate calculus, where I might be taking multiple different partial derivatives with respect to x, y, or z, where I'm indexing the x, y, and z components with this x sub I ranging from 1 to 3 in this particular case. So if you like, I can represent this all in terms of vector notation over here, equivalently index notation over here, just to reconcile which components are actually having derivatives taken with respect to what. Now, what's interesting is that I could rearrange some of the terms appearing in this expression. And I could also note that this term, the divergence of the stress tensor dotted with this virtual displacement field, is nothing more than this kind of interior term here. I'll kind of actually wave my mouse around there. So if I wanted to, I could actually rearrange this expression, and I could take, this term being equal to this term minus this term, which is precisely how we arrive at this kind of second step. We've enforced this product rule of differentiation, and we've rearranged some terms just to be able to get rid of this term that involves the divergence of the stress tensor. And you might say, oh, well, that's great, but now we have this term that involves not just the divergence of the stress tensor, it's the divergence of the stress dotted with, this virtual displacement vector. So what did that get us in the end? That didn't really help us move towards trying to get rid of having some divergence of some object. We still have to have that object being differentiable. Well, the advantage of doing this is that we can actually now enforce some other identity that you have already been exposed to, and that is precisely the divergence theorem. It's the equivalent of the fundamental theorem of calculus, and it was the thing that we actually used to derive the governing differential equations of equilibrium in the first place. Effectively, if you remember the fundamental theorem of calculus, it gave us this relationship between the integral of some derivative of a function between some limits a and b is equivalent to just evaluating that same function f at a and b, but with corresponding plus or minus signs attached to it. The divergence theorem looked kind of similar. The integral over the interior domain of some, domain omega involving the divergence of some vector valued function f, let's say, with 3 components, was equal to equivalently the integral of that same function, but evaluated on the boundary of this domain omega. So effectively, if I have some integral over some volume involving the divergence of a vector, I can convert that expression into this equivalent boundary integral. And that's precisely what we do to convert this term involving the divergence of the stress tensor dotted with the virtual displacement vector. I can use the divergence theorem to convert this particular term into an equivalent boundary integral. So an integral over the boundary of omega. So we have applied the divergence theorem, again, written here in index notation just for the sake of comparison and to reconcile which components are being multiplied with which other components in these different, multiple tensors and vectors appearing in this expression. And pardon me, but I think this expression involving VI, that should be an NI, pardon me. So NI being the normal to this boundary, so the surface normal aligned with a particular differential surface element. Okay, so we've manipulated things into this slightly different format, and notably, in taking this step, we've gotten rid of having to, use some divergence of a term involving the stress tensor. So we've gotten rid of the differentiability requirement on the stress tensor by manipulating things into this format. Now we have to take a little bit of a break and say, well, if I'm defining this virtual displacement function
which could be an arbitrary variation or some arbitrarily chosen virtual displacement function, we still have to impose a few requirements on what this virtual displacement looks like. It should be kind of like the displacement field in the sense that it should be also a continuous function. So that much needs to be the case. It should be a continuous function, and also it needs to satisfy these additional boundary conditions. Wherever we have specified the displacement on the boundary of this domain, so in particular, if we've specified the displacement along gamma u to be equal to u bar, then also along that same boundary gamma u, we have to specify the value of this virtual displacement field as being everywhere equal to 0 along gamma u, such that if we were to sum up the values of u plus v along gamma u, then everywhere along gamma u, we should still recover this kind of condition that the sum of u plus v is equal to u bar. Okay, that's basically saying that if we were to have some original displaced solution, u, which satisfies these displacement boundary conditions, then if we were to maybe try to perturb this solution away by some small virtual displacement v, then whatever virtual displacement or perturbation we make to that solution should still satisfy the resulting displacement boundary conditions that we've imposed on u. So that's kind of why we have to impose these homogeneous essential boundary conditions are what they're called on v. So v has to be equal to 0 wherever we're specifying displacements on the boundary. Okay, now that we have that, and revisiting that expression that we had derived on the previous slide, now we need to make a few substitutions, further noting that this exterior boundary of the domain, del omega, really is comprised of those two subsets, those two portions of the boundary, gamma u and gamma t, over which I'm prescribing the value of displacement at some discrete locations, and also the portion of the boundary where I'm prescribing the value of traction on the exterior boundary of this domain. Additionally, I'll go ahead and actually define some new quantity, which I'll call epsilon with a superscript v, which has the interpretation as being something like a virtual strain field, in much the same way that we can define strain as, you know, a tensor derived from the symmetric part of the displacement gradient. We could define this virtual strain field in much the same way as being the symmetric part of the gradient of this virtual displacement field. And if we do that, then we actually notice that, you know, if we make this substitution for the gradient of this virtual displacement field into this function, then it turns out that the symmetric part of this virtual displacement gradient, when multiplied with the stress tensor, itself a symmetric tensor, it actually doesn't matter whether or not I include or exclude the symmetric part of this virtual displacement gradient. It turns out that if this virtual displacement gradient happened to have some part that was not symmetric, then it wouldn't actually show up in this expression. So it's entirely equivalent to make this substitution. Okay, that's really just a notational nicety. But now we can actually come back and enforce some of our boundary conditions. First, we want to kind of simplify some of these expressions. And firstly, noting the fact that on whatever portion of the boundary where we're prescribing displacements, as we'd mentioned on the previous slide, on this same portion of the boundary gamma u, we are also saying that everywhere on that portion of the boundary, the virtual displacement function has to be 0 everywhere. So in effect, the virtual displacement function in this first term, the integral involving the integration over the boundary gamma u, that v should just be equal to 0 everywhere there. So this first term should really just go away. And this second term should also basically make things a little bit simpler by noting that everywhere on gamma t, where we're prescribing the value of traction, we can actually directly state that this term, sigma transpose dotted with the normal exterior normal vector on the boundary of this domain, that should be just directly equal to the traction vector which we've prescribed on the boundary. So in other words, we take whatever external traction boundary conditions and we plug them directly into this resulting expression for the weak formulation. And wherever we have, displacement boundary conditions, we can just get rid of this whole term. So by enforcing our boundary conditions and also kind of recalling our constitutive law for expressing the stress directly in terms of the strain tensor, we can make some further substitutions and arrive at this final expression, which, as you'll note, doesn't involve having to take any kind of divergence operators or derivatives with respect to, the stress tensor or anything like that. And we've actually directly included things like the external traction boundary conditions directly within this expression. So rather than kind of tacking on these additional requirements that, oh yeah, also we have to satisfy these traction boundary conditions, now we've just said, well, take all those traction boundary conditions and plug them directly into this statement of equilibrium so that now they're all nice and consolidated. Okay, so ultimately, taking all these things together and noting this final expression, the thing that we wanted, we can now pose the equivalent weak formulation of equilibrium now in this generalized 2D or, if you like, 3D domain. It doesn't really matter if you're considering this a 2D or a 3D problem. Ultimately, a lot of the same mathematics apply. The divergence theorem can be applied in either of those two situations. So we recognize that this equation, which is effectively an integral average statement of equilibrium, has to be satisfied for any arbitrary choice of virtual displacement function or test function V. And where we've defined these specialized sets of functions, this kind of calligraphic U and calligraphic V, such that automatically the displacement field has to satisfy our displacement boundary conditions. And also this virtual displacement field has to satisfy this kind of homogeneous essential boundary condition that V equals 0 on gamma U. Okay, so now we have this weak formulation of equilibrium. We've converted that governing differential equation into this equivalent kind of integral form of equilibrium. Now, what did we do next? Once we had things converted into this weak formulation, what was the next step in our process towards formulating finite element systems of equations? Well, have we taken care of the issue of there being still an infinite number of possible solutions that we have to, or candidate solutions we have to sort through? I mean, effectively, this still constitutes an infinite number of potential equations and an infinite number of solution variables we have to solve for. We haven't really made the problem any more tractable by converting it into this format. We've gotten rid of the differentiability requirements on the stress, but we still have an infinite number of equations we have to solve, an infinite number of unknowns. We have to make the problem smaller. And the way that we do that is by introducing approximations or approximate solutions. So, in other words, we have to pose some kind of Galerkin method or some kind of Galerkin approximation to this problem by choosing to represent the displacement field, and in fact, the virtual displacement field as well, not as these potentially, infinite number of material points that can deform independent of one another, but rather we can choose to represent the solution as being just the values of displacements at some discrete number of points. And to achieve that, we really have to figure out how do we pick these discrete number of points and how do we come up with ways of connecting the resulting disconnected domain that results from that discretization together. And the answer is finite elements. Well, we can do exactly what I just said. We can take our original domain omega and we can partition it into just a collection of simpler shapes. And specifically in this two-dimensional example, those simple shapes are really nothing more than quadrilaterals as shown in this example. Oh, we have one triangle here. Well, we'll give that triangle some credit. Anyway, so it could be quadrilaterals, it could be triangles, it could be any shape you like, as long as you can reasonably describe what happens over the interior of each one of these simpler shapes. Okay, so we discretize things into a finite number of these elements, these omega superscript E, which comprise some approximate representation of the solution domain. And we also have some finite number of these nodes, basically the vertices of these simple quadrilateral or triangular shapes that connect all of these different simpler shapes together. So that's kind of the extension of the finite element concept in these 2D or 3D domains. And the resulting discretization into these now 2D or 3D elements is sometimes called the finite element mesh. It's basically just the collection of elements and nodes all taken together and kind of meshed. If this were a simple grid in a two-dimensional domain, it'd be very simple to, just discretize this into a bunch of smaller cubes and kind of treat the solution as being, characteristic of variations of the solution within each one of those smaller cubes. Okay, so we've made the problem smaller. We've discretized our solid into a finite element mesh consisting of these elements and these discrete nodes. But now we also have to come up with some way of representing what the solution is, not just at those nodal locations, those discrete points. We also have to represent what is the displacement field in between these different nodal positions. And that was straightforward to do in the one-dimensional case, where we just said, well, if I have one linear segment and I know what the displacement is at this end and the displacement at this end, I can just linearly interpolate the values of the displacement of those two nodes. And it was simple enough to construct these interpolating functions that kind of gave me a way of representing the displacement as being this linearly varying function between those two endpoint values. But in this case, where we have slightly more complicated shapes, quadrilaterals or cubes in 3 dimensions, now we need slightly more complicated interpolating functions, which nonetheless satisfy some of the properties that we talked about when we discussed and introduced this subject of finite element basis functions. So, much the same way as we might proceed in any Galerkin method, we suppose that the solution, U, or rather an approximate solution that we will seek, can be represented as some linear combination of these so-called basis functions. These basis functions are really nothing more than, in the case of finite elements, these interpolating functions, which individually multiply some set of displacement coefficients, which in the finite element context have the interpretation as being the discrete values of the displacement at particular nodal points. Okay, so in other words, if we say that I know what the displacement is at each one of these different points, and if I know, some reasonable representation for these nodal basis functions, which might look, at least if I'm drawing as kind of like a contour plot, what exactly would this basis function associated with this node of interest look like? It might have a value of 1 right at this particular nodal location. That's kind of where the colors get a little bit darker towards the center of this, nodal location. And then it might ramp down to a value of 0 everywhere on the collection of nodes and along this exterior boundary where the colors start to fade out. So that's kind of the visual interpretation of what one of these basis functions might look like, such that it satisfies these two properties. And I think there was maybe even another one. But the main ones that I want to point out are that finite element basis functions have to be interpolatory. They need to actually recover the specific value of the displacement field when I plug in x sub I, basically. When I try to evaluate the displacement at this particular nodal location, I should recover precisely this discrete nodal value, which basically means that if I were to define these basis functions in this way, they should satisfy this condition, that they're equal to 1 at whatever node they're directly associated with. And at all other nodes, these basis functions need to be equal to 0. So that's kind of the Kronecker-Dalton property, which is an essential requirement for these basis functions being interpolatory. And the other one is this partition of unity property. So if I sum all the different nodal basis functions together, then at any point in the domain, they actually always sum equal to 1. Kind of an interesting property. There's some nice things with that. The other one was this compact support property, not explicitly stated here, but the idea is that really it's only over this patch of elements to which this particular node is connected that this basis function is non-zero. And then over these other kind of elements where I'm not showing any color there, it's assumed that this basis function for this particular node is just equal to 0 everywhere in these other elements. So that's kind of the compact support property, which also had the added advantage of resulting in finite element stiffness matrices that had those banded and sparsity properties. Really nice properties for the sake of achieving good numerical efficiency. So those are finite element basis functions as they would extend into this 2D and 3D context. Now, basis functions are really the things that have to vary over the entire domain. But I was a little particular in saying that there's this other related concept, shape functions, which are really nothing more than the basis functions for a particular node, but defined over a specific element. So when I talk of shape functions, I'm really speaking of nodal basis functions, but restricting attention to some specific element. As shown here, I might look at omega E, this highlighted blue element, and I could look at what are the interpolated values of nodal displacement for just that one element, which entails just the 4 nodes connected to that element. And I could then express the interpolated representation of the displacement field as really just the summation over those 4 nodes connected to that single element and involving corresponding shape functions, n, representing the interpolation functions associated with each of these 4 nodes. Okay. So what I want to do is come up with some way of interpolating the nodal displacements at all 4 of these nodes, such that I recover all those nice properties, interpolatory properties, partition of unity. So the question is, how do I construct these basis functions? N1 through N4 for a single quadrilateral element in 2D, or in 3D, maybe a cubic element. That's the question. How do I come up with these interpolating basis functions? Well, in the case of, 1 dimensions, it was fairly straightforward. We can come up with these linearly interpolating basis functions that interpolate these 2 distinct values of the nodes. Over a quadrilateral domain, let's say, I might have these 4 nodes that I need to interpolate. And in the case of a 3-dimensional domain, this cube, now I have 8. So things become a little bit more difficult to swallow. But before we kind of dive into some of the details, I'll kind of point out that all of these different expressions kind of assume that these nodal shape functions are expressible in terms of spatial coordinates. They might vary as a function of position, x, y, and maybe z in 3 dimensions. But in general, we don't usually specify these shape functions in terms of these global coordinates, x, y, or z. We specify them, at least when we were formulating things in 1 dimension, in terms of some local parametric coordinate domain. Rather than x, we specified things in terms of xi, which had a normalized range between xi equals -1 to xi equals +1. So really, we're going to do something very similar in extending things into the 2D and 3D domain. But the challenge is actually figuring out what should those shape functions look like, such that they satisfy all these different properties. Now, it turns out that the shape functions for a 2-dimensional element can actually be constructed in a very simple way, just by noting the form of the shape functions that we've already determined for a 1-dimensional element. Recalling what those look like, we have nodes 1 and 2 might have these shape functions that are simply linearly varying and expressible in terms of this 1 parametric coordinate xi. Now, N1 is just 1/2 1 minus xi, N2 is 1/2 1 plus xi. And it turns out, in order to construct interpolating basis functions or shape functions over this quadrilateral patch, we can do something fun. We can say, let's define this patch, this 2-dimensional domain, as also being defined over some normalized ranges where maybe the local parametric coordinate and the x and local parametric y, which all respectively denote c, and eta, just for fun, we'll introduce more Greek letters. So xi and eta are kind of like the equivalents of the local parametric x and y coordinates of this 2D patch. And xi will range over -1 to +1, just as we had in the 1-dimensional case, and eta will likely range over -1 to +1. So effectively, we've defined a bi-unit cube, which has, a length of 2 in both this xi and eta dimensions. Now, in order to construct the shape functions, it turns out we can actually construct them in a rather simple way by saying that if I have, let's say, node 1, I can actually construct some interpolating function that varies as a function of both xi and eta by taking the product of 2 of these 1-dimensional shape functions, but whose arguments are respectively xi and eta. Now, you can rationalize how this would come about, but supposing that I have these particular chosen forms for these 1D basis functions, where the nodal basis function associated with N1 this particular node, located at a value of c equals -1 and eta equals -1. I can come up with the corresponding nodal basis function by taking n1, this one-dimensional basis function, whose argument is c multiplied by n1, whose argument is not c, but rather plugging in eta. And what I get is an expression that looks like that. 1/4 of 1 minus c times 1 minus eta. And you can verify that this is the case, that if I were to plug in c equals -1 and eta equals -1 into that expression, what I'll get is, well, you can go ahead and do the math, but 1 minus -1 is just equivalently 1 plus 1, or 2. And then 1 minus -1, for 1 minus eta, gives me 1 plus 1, also 2. So 2 times 2 divided by 4 gives back just a value of 1. So I actually verified that this n1 satisfies at least one of the conditions of the Kronecker delta property, that this n1 is equal to 1 at c equals -1 and eta equals -1. And if you were to go through the exercise of saying, well, what happens if I evaluate this basis function at the other nodal location, at c equals +1 and eta equals -1, for example, you can recognize that, in fact, this expression should be equal to 0 there. And in fact, as shown in this example, if I looked at n3, for example, the nodal basis function associated with this node 3, you'll notice that not only does it satisfy this property that that resulting basis function, n3, is equal to 0 at these nodes, it's also equal to 0 all along these edges that connect nodes 1, 2, and 4. So kind of an interesting set of properties. But ultimately, these set of basis functions in 2D can be further generalized to equivalent nodal basis functions in 3D, applying effectively the same concept. We can define, rather than just 2 parametric coordinates, we define 3 parametric coordinates, c, eta, and zeta, all 3 of which might range over some parametric normalized domain from -1 to +1. And we can construct the corresponding nodal basis functions for all 8 of these different nodes by simply taking products of the one-dimensional shape functions evaluated with their arguments being c, eta, and zeta, respectively. The resulting forms also look rather kind of simply extended from that 2-dimensional example, now involving factors of 1, 8, all of them, and involving the products of these different kind of 1 minus or 1 plus c, eta, or zeta. So that's kind of the 3-dimensional extension of these same concepts to obtain interpolatory shape functions expressed in terms of these parametric coordinates. We won't actually reap the benefits of this until a little bit later. We'll have to end the lecture here for today. But if you have questions or other kind of follow-up, feel free to come chat with me at office hours. Otherwise, I'll see you potentially on Wednesday, depending on the weather. But otherwise, any questions before we end it today?
Should be plus or minus theta.
So there's some heuristics to determine which of these should be which, to make this a little bit easier to swallow. I'll present that in the next lecture. I'll explain some of the details of how you would figure out whether this should be a plus or this should be a minus, for example. I think in some ways you can rationalize that on the basis of requiring that, let's say, n1 has to be equal to 1 at node 1, and it should be equal to 0 at these other ones. So in enforcing that requirement, you can figure out which of these things should be plus or minus. So that's one way. But really, there's another way that I think is quite nice. So I'll present that next lecture. Other questions? Okay, I'll see you on Wednesday, hopefully, or not.